Survival for any biological organism depends on a vast, interconnected network pulsing with high-fidelity signals. Healthy cells continuously exchange chemical instructions to maintain the structural integrity of the surrounding tissue. The infinite descent paradigm identifies cellular aging as a recursive process of information degradation. Within this framework, aging occurs as errors compound within the organism's fractal-like structures, moving the system away from its initial state of order. As somatic cells replicate, minute errors in proteostasis compound, injecting biological noise into the system. Proteostasis is the high-dimensional network of pathways that regulates the synthesis, folding, and degradation of all cellular proteins. This chart tracked the resulting decline in the cell's signal-to-noise ratio, or SNR, a metric measuring the strength of a desired signal against background metabolic noise. As the SNR drops, critical regulatory pathways like Wnt and Notch fail. These conserved networks dictate how cells specialize and repair. Once the signal-to-noise ratio crosses the 1.0 threshold, the cell becomes functionally blind, unable to distinguish homeostatic cues from internal metabolic static. Crossing this threshold represents a point of no return. Internal cleaning mechanisms stall entirely, transforming the cell into a permanently clogged unit that propagates dysfunction to its neighbors. Because these clogged units are beyond repair, the Regional Cellular Reconstitution Strategy, or RCR, abandons systemic restoration. Instead, it utilizes a ship of Theseus approach to biological engineering. RCR focuses on physically removing the most degraded iterations of the biological fractal and replacing them with high-fidelity units, focusing on one localized region at a time. Managing aging requires shifting focus from repairing a broken machine to systematically deleting and replacing collapsed data nodes within the biological network. Visualizing this failure requires moving from the tissue level down into the microscopic interior of a single senescent cell. The physical driver of cellular entropy is liquid-liquid phase separation, or LLPS, a process where cellular components condense to form dense, immobile droplets. During LLPS, the p62 adapter protein transitions into dense, left-handed double helical filaments. High-resolution imaging reveals these filaments possess a structural pitch of 150 angstroms. This helical agrosome acts as a signaling black hole, creating a physical trap that sequesters proteins floating within the cytoplasm. The structure specifically captures vital regulatory proteins, such as beta-catenin, using a dimeric globular domain called the FIP200 claw. This physical sequestration creates a localized signaling blackout. By trapping beta-catenin, TQSM severs the cell's connection to the homeostatic instructions sent by the rest of the tissue. A cell trapped in this state cannot simply manufacture the enzymes required to clear the p62 aggressome because of a strict stoichiometric mismatch in its translation machinery. Proteotoxic stress normally triggers the integrated stress response, or ISR. This biochemical pause downregulates global protein production to give the cell time to recover. In human cells, the protein complex EIF2 exists in a 30-fold molar excess compared to its exchange factor, EIF2b. When stressed, the cell phosphorylates a fraction of the EIF2 pool. Phosphorylating just 10% sequesters every available unit of EIF2b. This results in a terminal zombie state. The cell remains biologically alive, but is mathematically barred from restarting the machinery required to clear the aggressomes. The cell is caught in a trap where it lacks the biosynthetic capacity to manufacture the chaperones and enzymes needed to resolve the very stress that triggered the pause. Since internal restoration is locked by mathematics, the RCR protocol initiates an external regional replacement. Phase 1 involves priming the regional mesenchymal stem cell niche. These MSCs are the factory for new tissue, but they naturally lack the replicative stamina required for large-scale replacement. To overcome this, we deliver nucleoside-modified RNA encoding human TERT over 3 pulses. TERT is the catalytic subunit of the enzyme telomerase, maintaining chromosome ends. This protocol extends telomerase by 0.9 kilobases, providing an additional 28 population doublings without permanent oncogenic risk. Phase 2 deploys nanobody drug conjugates, or NDCs, synthesized via a megamolecule approach. NDCs are targeted agents that combine a specific antibody fragment with a therapeutic payload. These agents use logic-gated avidity. In healthy cells, p62 exists as a single monomer with low binding affinity, causing the NDC to bounce off. In clogged cells, the dense helical agrosome provides high avidity, letting the NDC's arms lock securely into the helix. Once bound, the NDC releases a BH3 mimetic, which is a small molecule that triggers programmed cell death. This forces terminal apoptosis strictly in units that are already mathematically unsalvageable. By engineering a switch that only detonates upon encountering a high avidity helical agrosome, we eliminate the risk of systemic toxicity. Removing senescent cells creates a structural vacancy. If too many cells are cleared simultaneously, the tissue architecture will collapse before replacement units can arrive. Tissue stability is maintained by treating biology as a fluid dynamics problem, ensuring the targeted clearance rate of the agents matches the replacement flux of the stem cells. This 3D free boundary model tracks the shrinking volume of the aged tissue core. The clearance rate mathematically dictates the shrinking velocity of this necrotic core. As agents remove aged iterations, primed stem cells track the retreating boundary, expanding inward to maintain structural carrying capacity. The nano-agents coordinate this handoff by releasing a triple signal sequence. SDF1 homes the stem cells, HGF triggers their rapid expansion, and PDGF integrates them into the matrix. This sequence transforms tissue rejuvenation from a biological hope into a problem of rigorous, predictable control theory engineering. This precisely tuned replacement flex is designed for application to specific anatomical regions, rather than the entire body at once. In the aging heart, the protocol is administered via isolated limb perfusion microcatheterization, allowing for a concentrated, slow flush of metabolic debris. Replacing senescent cardiomyocytes with primed MSCs introduces youthful ligands to the environment. These chemical signals reverse the stiffness of the surrounding tissue, restoring contractile coordination. Applying RCR to the brain requires a different strategy for debris management, as the neural environment is highly sensitive to metabolic waste. Clearance in the brain is synchronized with the glymphatic system, which is the waste clearance pathway that uses cerebrospinal fluid to flush out metabolic byproducts. Timing the NDC-induced apoptosis exclusively during slow-wave sleep ensures that the resulting debris is removed without overwhelming the brain's unique drainage capacity. By localizing these interventions to specific regions, we can address the accumulation of biological noise where it is most severe. Systemic rejuvenation often fails because it ignores the physical laws of cellular phase separation and the mathematical lock of the stress response. RCR addresses the infinite descent by identifying the unrecoverable nodes within the biological fractal and replacing them with high-fidelity iterations. Resetting the biological fractal one anatomical region at a time provides a scalable pathway for maintaining biological resilience over a lifetime.